Most AI video generators create a convincing illusion of space, but stepping inside dissolves the environment. There is no physical geometry, only flat, colored pixels. The engineering standard for generative worlds is moving past frames you can only watch. The new baseline requires explicit, engine-ready meshes. Tencent's Hunyan team recently published a framework designed specifically to hit this standard. They call it WorldClaw. The system requires only a single, open-ended text prompt to initiate its entire construction process. The output arrives in two distinct parts. First, the framework generates independently editable textured meshes. This means every tree, building, and rock is an isolated 3D object. Second, it produces an explicit terrain base. The system assigns precise spatial coordinates, mapping exactly where those individual meshes sit on the ground. This entire assembly happens natively inside a standard version of Blender 5.1.1. Video generators lock their outputs into flattened, unchangeable video files. If a generated house has a window you don't like, your only option is to re-roll the entire prompt. By separating the individual geometry from the terrain floor, the output immediately slots into standard game engine workflows. You can grab that house, delete the window, and drop it into Unreal Engine. The catch is that no one in the industry has actually proven a pipeline like this can run reliably. Even Tencent themselves have not yet shown that producing these explicit environments can be done affordably at a large scale. By producing separated geometry and terrain, the framework provides a template for integrating generative content into existing asset pipelines. Watching a generated video is a passive experience. Editing a generated mesh is an active, production-ready workflow. A technical artist opening a WorldClaw file can select a specific asset, duplicate it, drag it across the map, and smooth out the terrain beneath it, using the exact same tools they use today. The deliverable format is correct. The tension driving this research is whether an automated production pipeline can actually survive contact with reality and deliver those assets without crashing. We previously analyzed why large-scale AI world models begin to hallucinate over long time horizons. Those models drift because they are trained to predict the next pixel. They do not maintain a permanent game engine state behind the camera. WorldClaw approaches the problem by constructing an explicit scene graph. It stores the exact coordinates, scale, and properties of every object. Instead of training a monolithic 3D world model to guess what a landscape looks like from a new angle, the system builds the permanent state directly. When you turn the virtual camera, the geometry is physically there. To keep tracking how frontier research solves these exact bottlenecks, hit the subscribe button below. By refusing to learn a 3D generative prior, WorldClaw correctly shifts its intelligence. It relies on orchestration, rather than trying to force a neural network to simulate physics. This flowchart maps WorldClaw's coarse-to-fine mechanism, organizing generation into strict phases. Phase 1 starts with planning agents. They translate the prompt into a structured scene specification, branching into regional zoning, terrain requirements, and object categories. Phase 2 takes that data and builds the global terrain foundation. The system generates semantic layouts, essentially 2D color-coded maps, dictating the exact physical boundaries of the environment. It applies reusable assets and procedural materials to that base layout, creating a walkable surface. Phase 3 scans that foundation and selects detail-demanding regions for specialized generation. The system generates 2D image compositions of those specific areas, constrained strictly by the underlying terrain conditions it already built. Those flat 2D compositions are extracted and reconstructed into 3D meshes. An external tool called SAM3D handles the precise segmentation and initial 3D reconstruction of these objects. A second tool, Hunyan 3D, executes high-fidelity surface refinement on those assets. The logic driving those Phase 1 planning agents comes entirely from Anthropic's Claude Opus 4.8, and the 2D imagery driving the regional compositions is generated by OpenAI's GPT Image 2. Tencent is effectively renting U.S. frontier intelligence to do the heavy lifting, rather than relying on their own native models. WorldClaw functions as an orchestration layer, separating global planning from local detail to prevent memory collapse. The final architectural step is a perception action loop. Render-based agents take virtual cameras inside the Blender scene, capturing 2D screenshots of the generated geometry. They scan for precise structural errors, specifically targeting scale inconsistencies and implausible object orientations. They isolate specific contact failures, meshes floating above the ground, excessive penetration into the dirt, and unstable physical support. Using frontier language models to visually critique and mathematically correct an explicit scene graph is a design pattern worth stealing, regardless of WorldClaw's ultimate success. The title of the paper claims agentic generation at scale. The contents of the paper present a different reality. This list tracks the quantitative evaluation metrics presented by the authors. There are 0. They report no FID score to measure visual fidelity. There are no human user studies to validate navigability. They omit the pipeline's overall success rate. They provide no data on per-scene compute runtime. And there is 0 documentation on the API dollar cost per scene. Without proper ablations isolating the 5 different stages of the system, it is impossible to determine which specific modules are causing inference latency. The actual evidence offered in the paper consists entirely of 11 hand-picked demo scenes. The document features exactly 1 qualitative comparison metric, a side-by-side walk view in Figure 8. That comparison relies on prompts specifically selected by the authors. It also relies on camera paths explicitly drawn by the authors. Cherry-picking a visual comparison against implicit systems like WorldGen and Sin City proves that explicit states look sharper from specific angles. It does not scientifically invalidate those prior methods. The document Tencent published is a highly curated portfolio of successes. It is not a rigorous scientific evaluation of a scalable system. The stated hardware requirement for the framework is a server running 4 export-compliant NVIDIA H20 GPUs. Paradoxically, that local GPU compute is actually the cheapest and most reliable component of the entire stack. The true vulnerability is the pipeline's total dependency on rate-limited, expensive, terms-of-service-bound APIs from OpenAI and Anthropic. The authors admit the difficulty of their own approach. Consistently translating natural language into stable, executable Blender code is remarkably difficult. Errors in code generation routinely cause visible scene defects, and node connectivity failures stall the pipeline, requiring manual human cleanup to proceed. WorldClaw demonstrates that maintaining explicit state over pixel prediction offers a viable path for asset creation, even if this specific API-dependent architecture is too fragile for a production environment.